So welcome to 1007 ICT, 1807 ICT, and 7611 ICT Computer Systems and Networks. This lecture 3A is on digital logic and digital circuits. So previously we had a look at numbers, number systems, binary numbers. How do we represent information in a way that we can put it into a computer and operate with it? And the kind of operations we saw so far were things like addition and subtraction. Do we want to be able to do more things than just addition and subtraction? Yes, absolutely. And actually, we've only seen whole numbers, so we'd also like decimal numbers or fractional numbers, right? That would be more useful for us. So we'll see that as we go through the course. But we have got a basic way to store information inside the machine, and we've got a basic way to operate on it. So in this lecture, we're going to be looking at digital logic and these things called logic gates. We're also going to look at something called Boolean algebra. We won't look at that in any great detail, but we do need to talk about it because you will see things written in that particular language. We'll also look at combinatorial logic gates. And at the end of this lecture, you will have an understanding of these logic gates. You'll have learned about the truth tables, an understanding of the combinatorial logic gates and their truth tables. So at the moment, there's no processing based stuff. You're just learning about these things. Do you think we're going to apply these in one of the workshops fairly soon? Yes, absolutely. You're going to get lots and lots of practice at these. And actually your assignment will be based around this kind of stuff. So there'll be plenty of opportunity to get practical hands-on experience with this. So, in terms of digital logic, we talked about representing numbers, but the machine doesn't really work with numbers. Remember, it works with electrical signals, right? So we're representing electrical signals with a 1 for on and a 0 for off, actually. It's a little bit more detailed and complicated than that, so we've kind of got an abstraction or a model for it. And actually, all these digital computers are built with these low-level switches or logic gates. They take some inputs, they make a decision, and they give you an output. That's really what they're doing. And these gates operate on binary signals, and they have one of two values. They're either on or they're off. Now, it's not quite that simple, like I mentioned. We have a value between 0 and 5 volts. So 0 to 2 volts is used to represent 0 or off. So there's a range there. It's not just 0, right? 3 to 5 volts is used to represent a 1 or on. That's another range. There's a gap in the middle, 2 to 3 volts, which is not a 0, nor is it a 1. It's an indeterminate value, and usually we have to transition from the 0 state to the 1 state or backwards. Does that make sense? So we have this intermediate state. Okay, so we've complicated it a little bit, but basically you can still see it as 0 is off, 1 is on. You don't really at this level need to know too much about the actual electrical values for those things. So we have some basic logic functions, and they can be applied to binary signals, and here I'm just going to talk about them just initially, but I'll show you a diagram, hopefully that'll explain this a little bit more clearly. We have AND, OR, and NOT, and they're the basic ones you're going to see very, very often. So AND, output is true if all the inputs are true. You notice I'm using the word true now and not 1 or 0. So true is 1, 0 is false. So you'll see them referred to by different names depending on what we're trying to achieve. Okay, so before, in the last lecture, we were talking about numbers, so we talked about zeros and ones. Could we have talked about them as trues and falses as well? Yeah, if we wanted to, but it would not have been as easy to work with them as numbers if we did that. Does that make sense too? Okay, so AND, output is true if all inputs are true. OR, the output is true if any input is true, and NOT, the output is the inverse of the input, so the opposite. You can build more complex functions. We're going to look at these basic ones, and you can glue them together to make more complex things. And actually, you'll see fairly quickly that we can make fairly complex things by just putting them together in the right organization. So can you guys be quiet, please? If I can hear you, then you're interrupting everyone on the way from me to you. All right, so please don't talk. Thank you. What I'm going to show you is the basic idea here. Now, I already talked about AND, OR, and NOT, right? I'm just going to make this my little magic box. I don't know what's in this box, but I've got two inputs, A and B. They go through the box and I get an output, and I'm going to call it X, and you'll see this fairly consistently throughout the lectures. You've got two inputs, A and B, and the output is X. Start with two things and we compress it into one answer. Now this box, we have a range of things this box could be. We've already seen the words and, we've seen or, and what was the last one? Not. And later on we'll see NAND, NOR, and XOR. There's a couple others we'll see. There are other gates probably that you may run into if you look on the internet, for example, but we're not really too worried about those for this particular course. So these are the basic ones we're interested in. So looking at this, if I have this as a table, and we're going to call this a truth table, right? So this thing here is a truth table. And what it's going to show us is what we end up with for a particular set of inputs. So what are my possible inputs? Well, A could be 0 and B could be 0. Yep. If A is 0 and B is 0, what could X be? What are its possible states? It could be 0 or it could be 1. So it depends on what function we're working with here, whether we get a 0 or a 1. Yeah? What about when A is 0 and B is 1? The output could be a 0 or a 1. If A is 1 and B is 0, it could be a 0 or a 1. And if A is 1 and B is 1, it could be a 0 or a 1. So this is just the general case. This is what it could be. Each of these gates, like AND, will pick a specific set of 1s and 0s on the output. All right, so we're going to have a look at those examples. Another thing I just want to refresh for you guys is the reason I wrote these like this, 0, 0, 0, 1, 1, 0, 1, 1, what's the reason for that? Is it arbitrary? Did I just randomly write them in that order? Those are all the different states, and actually what I'm doing is I'm counting from 0 to 1 to 2 to 3. And I'm doing it in that sequence. And this is one of the reasons why it's important to do things in this sequence, because the truth tables will always look the same if you always do it the same way. If you do them in different orders, they might be technically correct, but it will be very difficult to look at one of those tables and see, oh, I've got every case. All right, I'll show you what I mean by that. There's a definite benefit to doing it like this. So I've just talked to you about the general kind of case, right? We've got this box, takes two inputs, gives you one output. What are some of the specific boxes? So we have here on this slide, we've got three different boxes, and, or, and not. These are the basic simple ones. So you'll notice that they have a name, and typically we write them in all capitals. They have a symbol, and so the symbol for AND is like a D, a capital D, with two inputs and one output. You look at the OR symbol. The OR symbol, it's kind of pointy, looks a little bit like a Star Trek symbol. All right, find a way to remember that for yourself. And then NOT is basically a triangle with a little circle on the end. So they all look different. Does that make sense too? So by looking at a diagram, you should be able to work out, okay, that's AND, that's OR, and so on. You'll see in the middle, in the green there's a Boolean expression. This is the Boolean algebra that we're talking about. It says X equals A and B. So this is like an English or a mathematical version using letters to describe that picture. Do you think that's useful? Probably in some ways. What it means is we can work on that expression and we can manipulate it. It's very difficult to manipulate a diagram, but in maths, what do you do with mathematical formulas? Right? You plug things in, you change things around, right? So you can do very similar things with this, and I'll show you some examples. And at the bottom is a truth table. So the truth table is all the inputs and all the outputs for that set of inputs. So let's have a look at what that means. We'll start with AND. And so AND. What did it look like? It had a big capital D looking thing, and an input of an A, and an input of a B, and then the output is an X. And we said that we're going to build a truth table, yeah? So why am I drawing this table like this? Well, there's an A, there's a B, and there's an X as an output. What I noticed before was that, well, I can count 0, 0, 0, 1, 1, 0, 1, 1. Will this always be the same this side of the table? Yes. If I count like this, it will always be the same, which is one of the benefits of counting this way, right? It's always a regular looking table. How does AND work? How does it work in English? Yes. Both have to be the same. If I say AND in English, I expect that both things are happening at the same time. Yeah. So let's just take the easy part here. They both have to be the same, and not just the same, but they both have to be on in this case. All right. So 1 and 1 will be 1. What does that say about the other ones? They will be off, because not both of these, like that's a 0, 0. There's no 1 here. Would you agree? There's a 0 and a 1. There's a 1 here, but there are not two 1s. There's a 1 and a 0 here, not two 1s. This is the only one where both A and B are on at the same time. Can you see how that works? So the easiest way to remember AND, you only get a 1 if both 1s. That's the easy way. That's one way to look at it. The other way, which sometimes may be quicker, is AND you get a 0 if any of the inputs are 0. So if you see a 0 on the left, the answer for AND will be 0. It has to be. Does that make sense as well? So either of those is fine how you remember it, but pick one. Right? Find a way to remember this stuff easily, because you tend to use this fairly often. So let's look at OR. OR has this little pointy looking thing. Same deal, A and a B, and there's an X coming out. And here is our truth table. Same writing. And OR in English. How does OR work in English? I do this or I do that, but typically I don't do both. Would you agree? Well, this OR is kind of not the English OR. I'll show you the English OR in a minute. But this one says, look, as long as you're doing 1, if there's a 1 anywhere, the answer is a 1. If you've got a 0 or both zeros, no 1s at all, the answer is 0. So again, you can look at this one and remember it in a couple of different ways. The first way is 2 zeros gives you a 0. That's one way. The other way would be, if you see a 1 anywhere, you get a 1 on the output. Does that make sense too? So the way I tend to remember it is I do them in pairs. So when I'm doing AND, I remember if I see a 0 anywhere on the input, the output is a 0. For OR, if I see a 1 anywhere, the output is a 1. They kind of go together. Yep. The last one, at least on that initial slide, is this one. NOT. Now, NOT's a bit special because you only negate or invert one thing. So we don't have a B, we only got an A, and like this. So our truth table is a lot simpler. There's no B. And if A is 0, you get a 1. If A is 1, you get a 0. It's the opposite. One thing that I'll just point out about this diagram that you'll see in other places, you see this little circle here? This is negation. This is the thing that says flip that bit, turn it into its opposite. So if you see that on another diagram or another gate, that's what it means. Another thing I'll show you, just really quickly, is if I have this, that's written as A with a bar over it. So in sort of the English, the formula version of it, it's an A with a line over the top of it. You'll see that as well. In particular, if I do this, A with 2 bars over it, it means not. Do it twice. And that looks like this. And then I've got something on the outside here, right, on the right-hand side. What is the thing on the right-hand side? Well, this one is not A, and this one is A again. It just undoes it. Twice, you end up with the same thing. 3 times, you'll end up with the opposite. Does that make sense? So we'll use that in a future slide. So I'll just point that out. Those are the basic 3 logic gates, AND, OR, NOT. The next couple we'll see are variations on these. And then there's one special one called XOR. So here we have this thing called Boolean algebra. And I know, like, probably we don't like maths that much, right? Lots of symbols. You may actually quite like it. I quite like it. But I know people sometimes don't find that that interesting. So this stuff, we use it to represent the pictures or the gates, the circuits, right? So we can make a shorthand for certain things. So I'll show you what I mean with this. There are some statements here on the left under the OR heading, and it says XOR 0 equals X, then XOR 1 equals 1, XOR X equals X, XOR not X equals 1, and so on. Yep. So let's have a look at what that's actually saying and why might we write things like that. So let's write the first one, x or 0 equals x. So what we're going to do, we're going to plug in some values, and you'll see that the basic way we manipulate these things is just put some values in and see what happens. So x is 1 bit, it can be a 0 or a 1. Would you agree with that? Yep. So 0 or 0 is 0. 1 or 0 is 1, apparently. If this statement is true. Well, let's look at our table, our truth table. And this is the OR table, right? So if we look at the OR table, let me just write it very quickly. OR is basically wherever you have a 1 on the input, you get a 1 on the output, right? So you can write that very quickly. So what is this saying? This one here, 0 or 0 is 0. Is that anywhere in my table? Yeah? That's this line, yes? Okay, so we have this one. And what about 1 or 0 as 1? That's this line. So this statement captures 2 lines of my table. Is that good or bad? It's good, right? I can write this in a shorthand. I don't have to write four lines to my table. At most, it looks like I'm going to have to write 2 lines. Does that make sense? So let's have a look at another one. On that other slide, there was another one that said x or 1 is 1. I'm not going to do them all. I'll just show you a couple of parts here. So what did we do previously? When we see something like this, how do we make sense of it? What did I do before? What did I do here? Yep, put in all the possible inputs that I can. Now this one, it's easy. There's only one input, but maybe sometimes there's more, right? So this one, 0 or 1. That's what it can be. So 0 or 1 is 1. 1 or 1 is 1. Which 2 lines of my table is this? 0 or 1 is that line. 1 or 1 is this line. Yep, so that statement gives me those 2. These 2 statements together capture all the possible input and output states for an OR gate. Yep. So I can write this as a shorthand. Again, we might not be so clear why we might want to do that, but if we want to manipulate these things, right, work with them in some way, can we do that easily with the diagrams on a piece of paper? Not really, right? We need some way to write it down and work with those, the values. So before we move on to the next little part, I wanted to show you one other thing. I want to show you how you can visualize these gates, I guess, in an easy way, because they seem possibly a little bit arbitrary how they work. So we have some analog versions of these. So if I'm working with an AND gate, so here's my power source, here is my wire, here's the first gate, here's the second gate, and here's a giant light bulb. Okay, so at the moment, I'm going to plug in my values. So this gate here is this is a 0 and a 0. They're both off. Is the light on? No. Okay. 0, 1. Is the light on? No. What about 1, 0? Still not. The last one, 1, 1. We get the light coming on. Can you see this is basically how the AND gate works? Or it's an analog of it, yeah? So just as a visual way to see that, that might help with just remembering which one's AND. So how does OR work? Well, very similarly, there's the power. Here is my logic. Here's my light bulb. And we'll do the same thing. So they're both off at the moment. That's 0, 0. Do I get a light bulb on? No, there's no power flowing through. But if I do this, 0, 1, do I get light? Yeah. What about 1, 0? Should get light because there's a way through. And then 1, 1 will get light because, again, there's a way through. So again, as a visual way to represent this, you could imagine that this is how it works. Does it really work like this? Not really, but it's a visualization for it. The last one I'll show you really quickly is OR. Sorry, not. So not is a little bit more tricky. So here, let's say, is my power. I'll just point out that my drawing is terrible, so just bear with me. I think I can get the point across, but I'm probably not an artist. So here's my NOT gate. That's one side, and here is another side. And there's some relationship between these two sides. So I'll just show you this. If I have this one closed, right, this is a 1, there's a stick or something hard that holds this one a certain distance away. So at the moment, my value here is a 1 and this side is a 0. Would you agree? Is there any light? No. What about, remember the stick's still there, right? If I move this one here, then the stick is there, and it was like this, but because it's attached, it will close this one. So this one's open and this one's closed. Do I get power now? Yeah. So this is kind of inducing the result. Is it directly changing the result? You need two parts, right? Yep. So this one is a little bit more difficult to visualize, but you can see that if you have this kind of circuit set up, you can make one affect the other one. So if you have a 0 coming in, the other side will be a 1. If you have a 1 coming in, the other side will be a 0. It's opposite. Okay, so I wanted to show you just quickly a visual representation of those gates before we go into the next ones. So the next gates we have are NAND, NOR, and XOR. They look very similar. NAND looks like AND, would you agree? It even sounds like AND. NOR looks like OR. What's the difference between an AND and a NAND? If you're looking at the diagram there, just below the NAND gate, a NAND is an AND with a NOT after it. Yep. And a NOR is an OR with a NOT. Now you might be tempted by the name to say NOT AND, because it's NAND. Don't do that, because that's not what's happening. Right? If you say NOT AND, that means you have a NOT gate and then an AND gate. Is it actually a NOT gate and an AND gate, or the other way around? It's the other way around, right? It's an AND gate and a NOT gate. So, let's have a quick look at these guys. So a NAND gate I'll just write really clearly here, AND NOT. And the way it looks is it's an AND gate with a NOT gate after it. Do you remember I mentioned that the little circle is a NOT? And what it looks like is this. Yeah, so the little circle is basically the NOT part. So the truth table, you can remember this if you want to, like you can memorize it. I don't tend to memorize it. What I tend to do is just work it out from first principles. So what we're interested in, right, is we're interested in this one. Yeah? So it's AND NOT. Would you agree with that? So if I do an AND, it's ABX. Correct? That's what we've been doing so far. If I do a NAND, it should be AB not X. The opposite. Does that make sense too? Because it's AND NOT. So what I'm going to do first to generate the answer to this is I'm going to work out, well, what's just a normal AND, and then I'm just going to flip the bit, right? Just make it the opposite. So AND is pretty easy, hopefully, by now. This table is the same, this part of it. 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. That's great. That's not actually the answer that I'm looking for, but it's on the way to getting to not X. Because now I have X. What's not X? It's just the opposite, right? Then I can cross out this column. So what I'm pointing out is I can generate NAND using AND anytime. I don't have to spend my own memory to remember that part separately. You can do that if you want to, but there's a lot of stuff to remember, right? So I guess choose carefully. So that's NAND. The other one was NOR, and you'll see it's very similar. So NOR is OR NOT. So it looks like this, the little pointy one with that thing. And what it looks like is that. So our truth table What do you think? I'm going to do the same thing? Because it's just easy. So let's have a look. This part, do you notice that, do you think I'm even thinking about that part of it? I don't have to worry about it, it's always the same. So you can memorize that part. And actually, you're just counting from 0 to 3 in this case. So what was OR? 0 or 0 is? 0, 0 or 1 is? 1, 1 or 0 is 1, 1 or 1 is 1. So if I flip each of those bits, I'm going to get 1, 0, 0, 0, and that's my NOR gate. Okay? Again, I can generate it just by understanding what OR is, because it's just the opposite of OR. Then the next one, XOR, this one here. You'll notice it looks a little bit different. It kind of looks like an OR gate with an extra line in front of it. Yeah, so let's have a look at that one. This is the only odd one out, by the way, so I'll talk to you about that in a minute. But let's have a look at XOR. It looks like this. Right? And you'll notice that I'm not saying it in terms of any other gate. It's just its own gate, its own version. So before we do anything, I just want to put down the bottom here, just for our reference, the OR gate. Right? Because it's XOR, so do you think it's related to OR in some way? Has a similar name, right? So let's have a look at it. A, B, X, 0, 0, 0, 1, 1, 0, 1, 1. And then the X will be, yeah? Now before I talk about XOR, I'll talk about the problem that we had with OR. Do you remember when I asked you about OR in English? Right? So in English, if I say I'm going left or I'm going right, well, let's say that this is right and that's left. Yeah, I'm going right or left. This one is saying I can go both right and left at the same time. That makes sense in this gate. Does it make sense in English that you can go both left and right at the same time? No, you have to choose one or the other, right? So what we're actually talking about in English is the exclusive OR. You can go left or right, but you cannot go left and right at the same time. So slightly different purpose for this one. So if that's the case, we should be able to write XOR like this. Okay. This is right and this is left, let's say. And so you would expect these to be a 1. You can go left or right, and these should be zeros. You can't go no direction, right, or left and right at the same time. So that's the English explanation. I think it's fairly intuitive, and it's different from our standard OR. Right? The standard OR is really inclusive. You can do pretty much whatever you want. The exclusive OR is saying, well, actually, no, there's a limit on what you can do. What about looking at it a slightly different way? You'll see here, for XOR, when both inputs are 0, you get a 0. When both inputs are 1s, you get a 0. Is there any relationship between these two? They're both the same. If both inputs are the same, you get 0. If both inputs are different, you get 1. That's another way to remember it. That may be the easier way to remember it when we're working with these things. Whichever one works for you, right? Okay, and that's actually really powerful and useful. It's really useful to be able to see if one bit is the same as another bit, or if it's different from another bit. It comes up in a lot of different problems. So those are our 6 logic gates. Now we go to Boolean Algebra 2, the second set of rules. So the first set of rules, they were pretty basic, I think, but they weren't very powerful. We could describe a truth table fairly easily. This one is a lot more powerful in terms of what it's showing you there is on the left, you've got the OR form of something. On the right, you've got an AND form. And we can change how we write our gates or manipulate the equation or the formula that we're working with to turn something from an OR gate into an AND gate. Is that something that might be useful to us? What do you think? Probably, yeah. And it might be useful because AND gates, for example, might be cheaper to build or easier to build or whatever than OR gates, or the other way around. Right? So if we have a particular gate that's cheaper, we would like to convert our a circuit or our equation in this case into the right format. So there's a little bit of discussion we'll do about this, but looking down the bottom, you'll see on the bottom left there's a NOR gate, or an OR with a negation at the end of it, and then an AND gate with two inputs negated. And they are the same, actually. They don't look the same, just looking at the picture, but they are actually the same. So there's up the top here, there's an OR form or an AND form that we'll have a look at. When we see something like that, and I already mentioned this to you before, what we tend to do, at least at this stage, is we will plug some values in. So I've got an X and a Y, and they will range from 0, 0, 0, 1, 1, 0, 1, 1. So they go through all the possible values. Then that statement said X or Y in brackets and this bar over the top. What does the bar over the top mean? Not. So the brackets means do this first, and then what you get is flipped, right? Do the opposite of it. And that was apparently the same as not X and not Y. Apparently. So what we'd like to do is confirm this. And how would we do that? Plug some stuff in. See, right? So, well, X and Y can be 0, 0. So X 0, Y 0, if you OR them together, what do you get? 0 or 0 is 0. This negation here says this becomes a 1. Yep. On the right hand side, not 0 is 1, and not 0 is 1. 1 and 1 is 1. Are they the same? Yes? We're happy with that? Can you see what we did? We just plugged some values in and we just checked. Is it the same? Great. 0, 1. So 0 or 1 is a 1, and you flip it, you get a 0. Is that the same as, well, this is not 0, which is 1. Not 1 is 0. 1 and 0 is 0. Are they the same? Yes. What I'd like to invite you to do is try something like this yourself. Just plug them in. Obviously we're going through it fairly quickly now, but on your own time just go through it and you'll verify that it works the same way. You might want to be very careful about how you lay this stuff out, right? Because it's going to be very confusing if you don't lay it out nicely. You have a question? That's correct. The brackets go first. So the things in the brackets, you do the X or the Y first, and then you apply the negation, which is across the top here. Yep. So the next one is 1, 0. 1 or 0 is 1. 1 or 0 is 1. We flip it, we get a 0. 0, so not 1 is 0 and not 0 is 1. 0 and 1 is 0. Are they the same? Yes. And the last one, 1, 1. 1 or 1 is 1. Flip it, you get a 0. Not 1 is 0. Not 1 is 0. 0 and 0 is 0. You get the same thing. What has this achieved for us, going through this example? Do you now believe that this is the case? Yes? Yeah, we've just shown that actually, yeah, that statement is true. What that tells us is that I can have an OR gate and I can convert it into an AND gate. That's what we're trying to achieve. So the next little bit that's going to be a little bit interesting for us, and this will come up in a couple of places. So let me just grab this one. So you see here the OR form. Actually, just want to highlight this part. I have here a NOR gate, and NOR is what gate? Or not, yeah? And I can turn it into an AND gate. And what do these circles mean here? They're negations. The AND gate is not negated, but the inputs are negated. You see that? So it happens before you get to the gate. And those two things are apparently equivalent. Yep. And it's also saying here that if I have a NAND gate, it's equivalent to an OR gate with its inputs negated. Again, you can try this stuff out. There's statements here saying this is the case. I've shown you how to work through those, so please do if you're curious about that. But the thing to take away is we have a way to go from OR gates to AND gates. And that's important for this slide, because if we look at this truth table, we can see that the XOR function can be described as x equals a and not b, or not a and b. And it seems quite wordy, but that's what that's saying. When you see one of these, what do we normally do? Or what have I been doing? Do I expect you to just take it on faith that it's correct? No? What do? We plug some numbers in, we have a look at it. So guess what we're going to do? Plug some values in and we'll have a look at it. So the statement was we have an A and a B. And then it said A and not B in brackets, or not A and B equals, and we said it was XOR, right? So X actually in this case. That's what that statement was saying. Well, we'll do the same thing. What values can my A and B have? Well, we'll start with 0, 0. Also could have 0, 1, 1, 0, and 1, 1. And let's plug them in. So 0 and 1 is 0. Or 1 and 0, 0 equals 0, right? So I think that's okay. And I think it's okay because if I look at XOR, what does XOR look like? Yeah? Is this one 0? That's that one? Is that correct? If the inputs A and B are 0, my output is 0. That seems to be correct so far. What if my input A is 0 and B is 1? 0 and 0 is 0. 1 and 1 is 1. 0 or 1 is 1. 1, 0. 1 and 1 is 1. 0 and 0 is 0. 1 or 0 is 1. Now the last one, hopefully you can already see that it's not going to be a 1 for the output because at least one of these values in here will be a 0, right? So let's have a look at it. 1 and 0 is 0. 0 and 1 is 0. 0 or 0 is 0. 0, 1, 1, 0. In my truth table here, 0, 1, 1, 0. Does it match? Yes. Can you see that this Boolean algebra, this statement, x equals a and not b, or not a and b, is an English-like way or a mathematical way to write what that truth table is representing. And you'll notice in this next set of diagrams that we want it in that English type form because we can manipulate it, we can change it, we can move stuff around. Just like what you do with a mathematical equation, you can move something from the left-hand side to the right-hand side, you can multiply it by something, we can do a similar thing with these. So that function, XOR, can be built in 3 different ways, it says that. I suspect there are more than 3 different ways you can build it, but there's 3 ways on the screen here. So let's have a look at it. I know this is a little bit sort of maths heavy, but this is where it gets a bit more interesting, hopefully. It's a bit more visual. You'll see on the left, we have here x equals a and not b, or a and b. So this is a and not b. Yep, a and not b. This is not a and b. And this is or. So that circuit is saying a and not b, or not b and a. Sorry, not a and b, I should say. That's our basic circuit. And we could leave it like that, but maybe we're not happy with it. Maybe we say, look, we can find a cheaper way to build this, a faster way. Yep. So what we can do is we can manipulate this thing on the left here. We can turn it into the thing in the middle. You'll notice there's some extra bars here. right? They're negations. And what we've actually done is we've taken this AND gate and we've made it a NAND gate. Now, if we do that without any other changes, we have changed the circuit. Would you agree with that? There's definitely a change. So what we've done is we've recognized that NAND, right, is the same as AND not. Yeah. And so what we're doing is this. So if this one is AND not, what is AND not going to be? AND again. Yeah. So have we changed anything with this one? We've added extra gates in, but the outcome will be the same by virtue of, well, we had an AND gate, we made it a NAND gate, and then we put a NOT after it, so we've basically done a double negation. It's just an AND gate. Okay, on its own, that seems like a silly thing to do, right? We've made more gates, it's more complicated to think about. Look at all these bars, right? It's much more difficult to think about. But this is an intermediate step. So what we'll recognize is if we see this one in the red circle here, this is the same as this one. And have we seen this one before? Yes, we have. And where have we seen it before? We saw it here. Do you remember this guy? And what's it the same as? It's a NAND gate. So the purpose of doing that manipulation is to go from this thing on the left to this intermediate stage, and now we have this guy on the right, and what are my gates made up out of? They're just NAND gates. So this circuit in some ways is simpler to think about. It's just one gate. We don't have OR gates and AND gates and so on. We've just got one single gate. And not only that, but the AND gate will be the cheapest one to build. So we might want to use this one over some other variation on these. All right. The key thing here is not what the output is, but you see the transformation that we applied. Okay, so obviously there's quite a bit of understanding behind that, but there's a couple of simple rules you can apply. And the key thing is you can turn AND gates into OR gates and backwards and forwards, but you will imply, or you will need to apply negation to do that. Okay, so we saw how the OR gate can be, or XOR gate can be built in 3 different ways and how to manipulate those things. You'll get a bit of practice with that in the workshops, by the way, so you have a view of that. This slide just shows you, look, we're talking about these AND and OR gates, right? They're really, really small. You're not going to be able to look at them and play with them and interact with them in any meaningful way. But you can buy these gigantic chips, and these chips, like you see, they're pretty big. At least you can pick them up and move them around and plug them into breadboards, for example. That AND gate, or the NAND gate there, has 4 NAND gates. There's a 4 version AND gate, a 4 version OR gate. So you can work at them at human level and plug and play with them and try them out, or get them to perform their task, as opposed to having this minute one. So you'll see these, and you can buy these. They're not particularly expensive. In the workshops, we will start playing around with some physical logic gates, like ANDs and ORs, and they're just little plug and play ones, so you get a hands-on feel for those. And it's, as I said, it's really difficult to do that with these things because they're so small, right? You're not going to be able to meaningfully interact with them otherwise. So where we're going with this is we're trying to build something called a logic unit. And a logic unit is a programmable logic that allows you to apply some kind of logic function to a set of inputs. And actually what that's saying is I've got some inputs. In this case it's A and B. And A and B, well, let's just look at A. A goes into AND, then it goes into OR, then it goes into XOR, and then it goes into NOT. And actually that happens at roughly the same time. One thing I'll point out about this diagram, you see this little diamond kind of shape? It's a solder point. It's basically saying those 2 lines are connected. As opposed to, you'll see that this line goes over the B line here. They're not connected. Right? So they don't interfere with each other. But you'll also notice that B goes into AND, B goes into OR, B goes into XOR. It doesn't go into NOT. Why doesn't it go into NOT? There's only one input, so you choose one, and typically we choose A, right? Well, what's going on here? If they all go into AND or XOR or not, then you'll get 1, 2, 3, 4 answers at the same time. Can you deal with 4 answers at the same time? No, you typically want 1. So this box here, this yellow one, you'll see this shape come up in a couple of lectures for the next couple of lectures. This thing here, its job is to say, well, which one do you want? How does it do that? Well, you tell it. You have 2 selection lines. There's 2 lines here, so with 2 lines I can have 0, 0, 0, 1, 1, 0, 1, 1. They're my possible values that I can have. Would you agree? So if I say here 0, 0, I will choose the one of these which is equivalent to the 0, 0 input. So let's say this is 0, 0, that's 0, 1, this is 1, 0, and this is 1, 1. So if on the input lines I give you 0, 0 here, which one will you choose? The first one, AND. If I give you 0, 1, 0, 0, 0, 1, you would get OR go through. So what you're looking at here is a complex logic system that does everything at once on the left-hand side, gives you all these answers, and then you choose one of the answers. Do you think a real logic system is a little bit more complicated than this? Yeah, you have other functions you can do. At the very least, you have addition, subtraction, multiplication, division. There's a whole lot of things that you could be doing. So this is a 4-input logic unit. You could have many, many more values. And that's where we're going with the next section. How do we build one of these? Okay, so in summary for this section, we had a look at the operation of basic logic gates, we had a look at combinatorial logic gates and truth tables. In the next section, we're going to look at more detail at the logic unit, the selection logic, how do we choose which one we want to use, the decoder, which we need to make sure that we can convert from our input lines to which one we want. So listen guys, we haven't finished yet, so could you please be quiet? I'm going to wait. So this happens every single time when we finish a lecture, right? There are people still listening. So if you leave, can you do it quietly and not talk to your friends? Okay, so we're going to look at the logic unit, selection logic, and decoder logic for next time. We'll also look at something called multiplexing and demultiplexing. And those are things we need to be able to do to make sure that this logic unit will be able to work effectively. So that is the end of this section.